Hello, students. We start off with our next chapter, that is the chapter of continuity and differentiability. And today's topic is continuity. Now, before we start off the chapter, let us first understand the chapter breakage, that is how we are going to deal with this chapter. So in the chapter breakage, we are going to talk about all the different topics that we are going to cover in this chapter, or rather all the topics that we have in this chapter. So once we understand this, we start off with our first class, that is the topic of continuity. So obviously we have continuity, then differentiability, then differentiation of explicit function, that is the normal derivative that we already know from our class 11. Then we have differentiation of implicit functions, then logarithmic differentiation, parametric differentiation, then higher order derivatives, and finally we have mean value theorem. So this chapter is divided into 8 different topics, and we are going to deal with all these 8 different topics in 8 different classes. So this is the first class of this chapter, that is on the topic of continuity. So let us begin. Now, what do we understand of the word continuity or continuous? Now, whenever we call anything continuous, it means that something without any stop, it is going on and on without any break in between. So similarly, if we apply that concept in case of mathematics, then definitely in mathematics also continuity would mean that something which goes on and on without any break. Now for us in this chapter, we are dealing with continuous functions, so we are going to talk about functions. So now, what do we mean by continuous functions? Well, continuous function means it is such a function when we plot the graph of that function, there won't be any break or a gap. So just to put in a simple word, any function will be called continuous if there is no gap in the graph of the function, and if there is one, then it will be called a discontinuous function. So now let us take an example and understand how this works. So let us take the first example. Let us take fx equals to x square. So now we know that this function x square, so for no value of x, we know that there are no discontinuity. Discontinuity means no gap in the function. How to understand there is a gap? Whenever for some value of x there is no value for the function, say there is a value of x for which fx does not exist, or a value of x for which the function gives an infinite value, not a finite value, those points are considered to be a gap or a break. So we know for fx equals to x square, there is no gap, and the graph of the function looks something like this. So you can see it is a continuous graph extending for all the values of x, so there is no gap. So therefore this is one example of a continuous function. Similarly, if I take another example, that is fx is equals to 5 minus x square when x is less than 2, and x minus 1 when x is greater or equals to 2. So now if I look into the graph of this function, we can see this function is also having a continuous graph without any gap in between. Now there is one small difference between these two functions. In the first one, we can see the graph is uniform. Uniform in the sense the graph does not have any sharp edge. There is no sharp edge in the graph. The graph is a smooth graph. Now whenever there is a concept of smoothness or a sharp edge, we are going to deal with that concept in the next class. But just for us to understand that these two graphs differs only in that one key point, that is, the first graph is a smooth graph and the second one has got one edge, sharp edge. Now where that edge is exactly at the branching point. So how to understand the branching point? The very point where the cases are different. So in this case, x equals to 2 is my branching point. So you can see before x equals to 2, the function was 5 minus x squared. So it is a parabola. The graph comes something like this till here, till this point. This point. And then after this point, the graph is a straight line, that is x minus 1. So doesn't matter what, these both the functions, they are continuous. Now let us define mathematically what does continuity means. So whenever we talk about continuity, we always talk about continuity at a point. So whenever we are talking about continuity at a point, it means a function is said to be continuous at a point. Say let the point be x equals to a. If the limit at x equals to a is same as the functional value. So limit x tends to a fx, that is my limiting value at x equals to a, and fa, that is the functional value at x equals to a. So this is basically what it is. Now what does limiting value means? Limiting value means what is the value of the function when it is approaching towards a, and f of a means the value of the function at a. So if both the values match, then we can definitely say that the function is continuous. Now how to understand that graphically? Let us move back. Let us just go back to our example. So you can see here, if I take any value, for the matter of fact, say let us take any value here. Now at this point, whatever that point is, we can see if we come from the left hand side or from the right hand side. So if we are approaching this way or we are approaching from the other way, doesn't matter what, we are getting at the same value, that is whatever the functional value at that point is, and therefore we can say that the function is continuous at that point. Similarly, if we take any value here, say let us take this value, particular any value, I don't know which point it is, but definitely I can see from left hand side also, from right hand side also, the graph of the function reaches that very point itself. So therefore I can say the function is continuous at that point. Now the only point which is going to be crucial is the branching point, because you see the graph comes from one side to the branching point and then goes the other side. So therefore at the branching point we need to see that if the left hand side also approaching towards the particular value, and also from right hand side also it is approaching towards the particular value. So now if we go back to our definition, that is a function to be called as continuous, then we understand this, that its limiting value and its functional value both must be equal. So now let us check for the function that if it happens or not. So let us take the first example, which is obviously fx equals to x square. So let us take any point. So let us take x equals to 1. So now let us check the continuity at this point. So if I want to check the continuity at this point, first I need to find out the limit at x equals to 1. So it is very easy for us to see that limit extends to 1 fx, which is x square, and that is equals to 1. Similarly, the functional value at 1 is also 1. So therefore, the function can be called continuous at x equals to 1, because the limiting value and the functional value both matches. Then let us take the same function and let us take a different point, that is x equals to 2. And we will see that if we calculate the limit, which is 4, and definitely if we see the functional value, that is also 4, and hence my function is continuous at x equals to 2. Now let us move to the next example, that is the other function that we took, that is fx equals to 5 minus x square when x is less than 2, and x minus 1 when x is greater equals to 2. So now let us take one point, let the point be x equals to 1. So let us try finding out or let us try checking the continuity at x equals to 1. So now again let us first find the limit. So limit extends to 1 fx is limit extends to 1 5 minus x square. Now how to understand why I am taking this 5 minus x square? Obviously you have to check where x equals to 1 lies. Now obviously I can see this branch is when x is less than 2, and 1 is obviously less than 2, so I will consider this branch. So now if I consider this branch, I can see that the limiting value of the function at x equals to 1, that is 4, and similarly if I see its functional value, that is also 4. So they both match, and as they match I can say that the function is continuous at x equals to 1. I think it is pretty clear. Now let us take another point for the same function, that is let us take x equals to 2. Now we have to understand this, that x equals to 2 is a branching point. Now obviously what does branching point means? Branching point means that the very point at which the curve changes. So I can see at x equals to 2, on the left hand side of x equals to 2 it was one curve, and on the right hand side of x equals to 2 it is another curve. So at x equals to 2 the curve changes, and by looking at the graph, how to understand that the curve changes? Obviously the very point there will be a sharp edge, that point is my branching point. So in any function, wherever you find there is a sharp edge, you must understand that that point is my branching point, for any function it be. So now to check the continuity at this point, first I need to find the limit. Now whenever I need to find the limit, that is limit extends to 2fx on a branching point, then I have to consider both the left hand limit and the right hand limit. We have already done this in our previous class. So let us try finding the left hand and right hand limit. So let us first the left hand limit. So left hand limit is limit extends to 2 minus, remember whenever it is left hand limit we put a minus sign on the top. Then limit left hand limit is limit extends to 2. Now whenever it is the left hand limit, I take the branch which is to the left of the branching point, that is the branch for which x is less than 2, that is 5 minus x square, and I can see that the limit value is 1. Now let us try the right hand limit. The right hand limit is x tends to 2 plus, and for x tends to 2 plus, obviously I have to take the branch which is to the right of 2, that is x greater equals to 2, and in for x greater equals to 2 I have x minus 1. Fine. So now in both the cases I can see that the limit value for both at the left hand side and at the right hand side, they are equal. And as they are equal, then I can say that the limit at x equals to 2 exists, and that is equals to 1. So therefore I can say limit extends to 2fx, that is 1. And now let us find the functional value at 2. Now the functional value at 2 is 1. Obviously we can see if we put 2 in x minus 1, obviously the value 2 lies here. So if we put 2 here, 2 minus 1 is 1. So functional value at x equals to 2 is also 1. So the limiting value and the functional value both matches, and hence I can say that the function is continuous at x equals to 2. So always remember this, whenever we have a function where there is a branch, and if I have to check for continuity at the branching point, then always remember that I have to find both the left hand limit and the right hand limit. Now, once we have understood what is continuity, now let us understand how to find discontinuity. Discontinuity means how to find the points where a function is going to be discontinuous. So now, before we go there, let us first understand, or let us know, which are the functions which will always be continuous. Always be continuous means for any given point, any point in the domain, that is for any value of x, the following functions will always be continuous. The first one is any polynomial function. So if I take any polynomial function, it will always be continuous. Why? Because any and every polynomial function, they represent parabola. Now obviously if it is a square, I mean it is a second order polynomial, then it represents a parabola, which we already know. And if it is a higher order polynomial, that is if there is a cube or to the power 4 kind of a term, it will also represent parabolas, but definitely those are higher order parabolas. We don't know, we haven't dealt with, but always remember that polynomials do represent parabolas. Now, next one is trigonometric functions. Now, all the trigonometric functions are continuous given they are within their domain. Why? Because if I take sin x and cos x, see, sin x and cos x is continuous throughout for any value of x. But if I take tan x, we know that tan pi by 2 and tan minus pi by 2, they don't exist. Why? Because they are non-finite values. But if I restrict the tan function in its domain, that is, we know that tan theta is possible only when theta belongs to open pi by 2 to pi by minus pi by 2. Just pardon my writing. So obviously if I take the angle in this interval, that is if I restrict my domain to this interval, then definitely tan theta is also continuous. Tan theta will also give me the graph of tan theta will be continuous. So not for all trigonometric function, but whenever we are considering trigonometric function, we have to be very careful with the domain. We have to understand what domain is given, and in the domain it is always continuous. But if I am given a different interval where we can have a point of discontinuity, then we have to check for that. Anyway, now again, inverse trigonometric function, the same way, not for all the function, for sine inverse and cos inverse, they are always continuous. But if I take any other inverse trigonometric function, say tan inverse, cot inverse, or any other, then definitely those functions will be continuous given they are taken in their domain. Next is exponential function. Now again, exponential function is always continuous. Throughout it is continuous for any value of x. If you take any value of x, it will be always continuous. Then logarithmic function, obviously logarithmic function, I need not separately tell you that it should be taken in the domain, but obviously I know logarithmic function does not exist for negative values, so I cannot take negative values of x. But if I take those values of x which are permitted for logarithmic function, then logarithmic function is also continuous, right? So now let us move to algebra of continuous function. Now algebra of continuous function means how two or more continuous function interact with each other. So if I take fx and gx to be two continuous functions, then I can say fx plus gx is also continuous. For example, if I take x square as fx and if I take 2x as gx, then already I know fx separately, that is x square, is continuous, and gx, that is 2x, that is also separately continuous. So if I add them, that is x square plus 2x, now which is evidently a polynomial function, so we can definitely say that that will be also continuous. Next, fx minus gx also will be continuous, which is obvious. Then fx into gx, that will be also continuous, no doubt about that. Now the only one, that is the fourth one, fx by gx will be continuous at all the points except at those points where gx is 0. So definitely if gx is not 0 at any point, then it will be continuous everywhere. But if there is a point where gx becomes 0, now you can understand, if gx in the denominator, any number or any function giving me a 0 value in the denominator, definitely at that point it won't be continuous. So leaving those points, the function will be continuous everywhere else, right? So now we move to discontinuity. Let us discuss about the discontinuity. So now, when to call a function discontinuous? Obviously when it is not continuous. But whenever we are discussing discontinuity, we need to understand that there can be discontinuity of three main types, right? So let us first take examples and understand. The first one, let us take as 1 by x square. So if I take 1 by x square, I can see if I put 0 in place of x, then it is not going to give me a finite value. It will become infinite. So therefore I can definitely say that x equals to 0 is a point of discontinuity, because the function doesn't give me any value at that point, or the curve breaks at that point. And if we just see its graph, it is very evident. Just look at the graph. You can see the graph is exactly similar. I mean, it is continuous till the point it reaches 0. So if I look here, see, the graph on the left hand side is all the way continuous, on the right hand side is also all the way continuous. There is no break in the graph. But at x equals to 0, you can see both the branch of the graph does not meet. If they would have met somewhere, then definitely I could have said the function is continuous. But you can see it does not meet at all. So therefore, x equals to 0 is a point of discontinuity here. I think it is very clearly understandable. This kind of discontinuity is termed as an infinite discontinuity. Let us come to that a little bit later. Let us take another function, that is fx is equals to x square when x less equals to 1, and 6 minus x when x greater than 1. So again, how to understand the function is discontinuous? See, whenever there is a branching, that means we understand the graph of the function is different on one side and it is different on the other side of the branching point. So at x equals to 1, how the graph is going to look? Let us just see the graph. it is going to look something like this. So how does it look here? See, the graph is all the way coming from here at x equals to 1, and again on the right hand side the graph is going from here. So that means what? There is a huge gap. You can see there is a huge gap here. The graph does not meet, both the branches of the graph does not meet. In the other case, in the previous case, in previous example, we saw that the left hand side of the graph and the right hand side of the graph, they met at same point. So therefore the function remained continuous. But here we can see that the graph of the function from the left hand side and the graph of the function from the right hand side, they do not meet, but there is a big gap. So this is also another example of discontinuity, but we can definitely see that both the cases, that is this case and this case, they are two separate cases of discontinuity, and that is one of the reasons why we have separate names for it. So the first one is called an infinite discontinuity. Infinite discontinuity means that the point where the function is discontinuous, the value of the function is non-finite. So that is called an infinite discontinuity. And this one on the right hand side, this is called a jump discontinuity. What is the meaning of jump discontinuity? Jump discontinuity means that the graph of the function has a break in between. Which one is the break? Hold on. Which one is the break? The break is, this is my break, or this is also called as the jump. Why jump? Because you see the value of the function at this point, that is here, and the value of the function here, there is a sudden spike or sudden jump in it. That is why it is called a jump discontinuity. Now always remember this, you can find jump discontinuity only if the function has a branch. If the function does not have a branch, you will never see a jump discontinuity. Jump discontinuity happens only when the function is in the form of branch. Now there is a third kind of discontinuity, that is called a removable discontinuity or a whole discontinuity. Whole is HOLE, whole. So let us understand how it happens. So let us take the function fx equals to x square plus 3x plus 2 divided by x plus 1. And how does the graph of the function looks like? The graph of the function looks something like this. So you can see for all the values of x except one value, the function is defined. You try putting x equals to 0, you try putting x equals to 1, you try putting x equals to minus 2, minus 3, minus 10, 100, 1000, whatever you put, you can see that the function gives you a particular value for it. But if you put x equals to minus 1, if you put x equals to minus 1, you see the function doesn't exist. And that is the reason why there is a hole. This is called a hole. That means as if like the whole function, the whole graph of the function is continuous otherwise, except at a one particular point where there does not exist any value at all. So that is why it has left a hole there, like a small gap. We call it a hole if there is only one point, and we call it a gap if there is a considerable distance. So therefore such kind of discontinuity is called a removable discontinuity or a whole discontinuity. Now why the word removable? Removable is obviously, it means that this discontinuity can be removed. How it can be removed? By placing some value at that hole. Now how to place the value at the hole, let us see. Now let us take example and understand all the three different types of discontinuity. Before that, let us define what these three types of discontinuity we have. So whenever we are discussing points of discontinuity, the first one, a function is said to be discontinuous at a point, or also we can say that that point is a point of discontinuity for the function if the limit is non-finite. Limit is non-finite, that means that it does not give you any finite value at that point in a limit. So therefore that is one discontinuity. Now the second one is jump discontinuity. Now obviously the jump discontinuity, from the definition itself you can understand, from the left hand side it is giving me one value, from the right hand side it is giving me a different value. So the left hand limit and the right hand limit of the function won't match. If they don't match, then we call that to be a jump discontinuity. And the third one, that is the removable discontinuity. Now understand it a little bit. When do I call a function having a removable discontinuity? If the limit exists, means that the function has got a limiting value, but it does not match with the functional value. That is one thing. Or the functional value does not exist or defined at all. So in the previous example, that is the example that we took, we saw that the whole function has got values defined for all the possible values of x except for one particular value. So at that point we can definitely say that the function is having a removable discontinuity. So now obviously when this is called a removable discontinuity, understand this, these two are also called non-removable discontinuity. Non-removable means those are permanent discontinuities which we can't remove, they will always remain. But in case of the third one, in the third type, we can always remove the discontinuity. Now how to do that we will be seeing in the example. So let us move to the examples. Let us take the first one, that is fx equals to 1 by x square, and let us try to check the continuity at x equals to 0. So at x equals to 0, we can see that limit extends to 0 fx, that is limit extends to 0 1 by x square, it does not exist. Why? Because if I put x equals to 0, then we can see that it is not giving me any finite value, and when any limit does not give a finite value, we say that the limit does not exist. And when it so happens, then I can definitely say that the function is not continuous or discontinuous at x equals to 0, or we can say that x equals to 0 is a point of discontinuity of the function f, right? Simple. So this is the case of infinite discontinuity. Next, example 2, that is this function. Now in this function, obviously the branching point is x equals to 1, so we have to check at x equals to 1. So at x equals to 1, we can see that as it is a branching point, I need to check both the left hand limit and the right hand limit. So now if in the left hand limit, we can see the limit, left hand limit, the limit is 1. You just do your calculation, you will see that the limit value is coming to be 1. But in the right hand limit, I can see the limit value is coming to be 5. So therefore it clearly does not match the left hand limit and the right hand limit, they does not match. And as they do not match, then definitely I can say that the function is not continuous at x equals to 1. So this is the case of jump discontinuity. Jump discontinuity will always be possible in case of branching functions where there are branches. And how to understand there is a jump discontinuity? We will see that the left hand limit and the right hand limit, they are not equal. Next, example number 3. So let us take that function, that is fx equals to x square plus 3x plus 2 by x plus 1. Now before we go into finding its discontinuity, let us understand how the function is. So I can write fx equals to x square plus 3x plus 2 by x plus 1 as x plus 2 into x plus 1 by x plus 1. Do your calculation, do the factorization. Now, as we have this function, this is how the function looks like. Now, you can say it's that why I am not cancelling out x plus 1 in the numerator and denominator. Well, obviously, if we cancel out the x plus 1 in the numerator and denominator, then that function and this function are not the same function. Why? The fact that because there is a x plus 1 in the denominator as well as in the numerator, this is actually causing this whole to come. See, if I put x equals to minus 1, then it doesn't give me any value. Why? Because there is a 0 in the denominator. And that is the reason why we have a hole in the graph. But if we would have cancelled this x plus 1, this one and this one, then what would have happened? Then in that case it would have been just x plus 2. In that case this function wouldn't have been exactly like this. So there wouldn't have been a hole here. So therefore always remember this, as the function is given, what did I do? As the function is given, that is this function and this function, they are not two same function, they are different functions. So therefore we can't manipulate and we cannot cancel this out. So always remember this. Now we can clearly see that f of minus 1 does not exist. I think I need not reason it out why. Just put minus 1 and see the value does not exist. And then if I try to find out the limit at x equals to minus 1, let us see what happens. So when I'm trying to find out the limit at x equals to minus 1, so now when I'm trying to find out limit, always remember, if it is limit, I can always think of cancelling this out. Why? Because limit means it is approaching the value minus 1 but never equals to minus 1. This is something we have already discussed in our previous class, that is in class 11, that limit means it is approaching towards the value. So it will never be at the value. So when it is not at the value, so therefore we can cancel it out. So if we cancel it out, what does it give? It gives me, obviously, limit x tends to minus 1, that is x plus 2, and that is equals to 1. So we can see that the functional value at minus 1 does not exist, but the limiting value exists, and that is equals to 1. So this kind of function is called, this kind of function is said to have a removable discontinuity at x equals to minus 1. Now, as it is called a removable discontinuity, this we can remove. Now let us see how we can remove. So we already just discussed this, that f is having a discontinuity at x equals to minus 1. Now how to remove this? So if I want to remove the discontinuity, then I have to redefine the function. Redefine the function in which way? In a way something like this. So if I redefine the function something like this, that the function will be x square plus 3x plus 2 by x plus 1 for x not equals to minus 1. So I have to mention this, that any value other than minus 1, the function may follow the given curve, the given expression. But at x equals to minus 1, I am fixing the value of the function to be 1. So if I fix the value of the function to be 1 at x equals to minus 1, then it solves my problem. Why? Because now we have the functional value at x equals to minus 1. Now from this definition I can say f of minus 1 is exactly equals to 1, and that is same as the limiting value here. So now the limit and the functional value, they match and the function becomes continuous. So what we actually did is that we actually filled in the value. We just actually did what? We just filled in this value by putting minus 1. So we filled the hole by putting that value there. So whatever that small gap there was, I intentionally put some value in order to make it look continuous. So therefore that is the reason why we call this type of functions to have removable discontinuity. Removable means that kind of a discontinuity which we can remove on our own, or which we can add on our own, as well as we can remove on our own. Right? So now this is more or less the chapter. Now let us discuss few problems and we will be done with it. So let us take the first problem. The first problem is, for what value of k the function fx, that is equals to tan 5x by sine 2x for x not equals to 0, and k when x equals to 0 is continuous at x equals to 0. So exactly this is another case of this is also, we can see this is also a case of, today I am getting disturbed. We can see that this is also another case of removable discontinuity. Why? Because for x not equals to 0, it is following a function, and at x equals to 0 we have to assign a particular value which makes it continuous. So now let us first find out what is the limiting value at x equals to 0. So let us try finding out this. So now we already know how to do this. So we do what? We divide by 5 by 2 and we multiply by 5 by 2, and also we multiply x both in the denominator, and that gives me the value 5 by 2. So the limiting value at x equals to 0 is 5 by 2. So therefore, if I assign this particular value at x equals to 0, that makes the function continuous. So therefore, my function to be continuous, obviously the limiting value and the functional value has to be equal, and therefore k will be equals to 5 by 2. So I think it is clear how we deal with such problem wherever we have to find an unknown quantity like k in the function. Next, problem number 2. Now in the previous problem we had only one unknown. Now in this problem we have two unknowns. So if the function f is defined something like this, that is 3ax plus b when x is greater than 1, and 11 at x equals to 1, and 5ax minus 2b when x is less than 1. And it is also told that it is continuous at x equals to 1. So you are already told that the function is continuous. Now to make it continuous, you have to find the value of a and b so that it happens. So now let us do it. Now again, we always need to understand and we always need to remember this, that the function is always continuous in its branches. So 3ax plus b, if I consider the branch, the function is always continuous in the branch, no matter what, because it is following one particular curve. But the only point where we need to check, that is at the branching point. So therefore, let us try finding out both the left hand and right hand limit here. So the left hand limit is limit x tends to minus 1 fx, that is limit x tends to 1, sorry, not minus 1, 1 minus, limit x tends to 1, 3ax plus b, that is equals to 3a plus b. And the right hand limit, that is, if we just do it, we are getting 5a minus 2b, right? Now at x equals to 1, the functional value is given 11. Now we know that for a function to be continuous, the left hand limit must be equal to the right hand limit, and that must be equal to the functional value. So we can write this. So the left hand limit, that is equals to the right hand limit, and that is equals to the functional value. So from here I can say 3a plus b is equals to 5a minus 2b, that is equals to 11. So it gives me two different simultaneous equation, that is 3a plus b, that is equals to 11, and obviously 5a minus 2b, that is equals to 11. I get these two simultaneous equation. Now once I get these two simultaneous equations, so now we can go on solving these two simultaneous equation to find the value of a and b. So just do your calculation. I haven't done it here, so just do your calculation and check. You get the value of a and b to be 3 and 2. So this is more or less the problem. Always remember this, that for any branching function, the function will always be continuous in its branches, in one of its branches. The only place where the continuity needs to be checked, that is at its branching point. And whenever we are checking continuity at its branching point, we have to find both the left hand as well as the right hand limit. Okay, so let us move on to problem number 3. The problem number 3 is given, examine the following function for continuity. And it is given fx is equals to x by mod x when x is not 0, and 0 when x is equals to 1. X is equals to 0. Now, in this problem, you see that it is a little bit different from the other problems. Why so? Because here there is no point mentioned. There is no point mentioned. In the previous problem it was mentioned it is continuous at x equals to 1, it is continuous at x equals to 0, something like that. But here you are just asked to examine the continuity. And whenever you are asked to examine the continuity, it means that you have to examine for the whole function, that is for all the points. Now obviously for all the point, it does not mean that you take each and every single point and you go on checking continuity, not like that. But you need to understand where I need to find, or where I need to check the continuity and where I need not. So now obviously I told you that whenever there is a branch, we need to understand that the only point where I need to check is the branching point, because leaving that point, in any other point, the function is always continuous. So let us first understand how this function is like. So we are given fx is equals to x by mod x when x not equals to 0 and 0. So now how mod x works, that is something we already know, but let us just revise. Now mod x is like minus x when x is not less than 0, and it is just x when x is greater than 0. So mod x becomes minus x when x is less than 0, and it just remains x when x is greater than 0. So definitely this function for x less than 0 would become x by minus x, and it will become x by x when x is greater than 0. Now just for a matter of fact, it's a small tip. Whenever you are given a mod function, always remember that it has a branching, and you have to first identify the branching and then write the function in the form of branches, and then you need to solve the problem in whatever the problem has been given. So now say for example, just for an example, I'm just doing this. Say you are given x minus mod of x minus 5. So if you are given mod of x minus 5, then first you need to understand where the branching is. How to understand where the branching is? The branching is exactly at the point where it is giving you the value 0. So mod of x minus 5 gives you 0 at where? It gives you at x equals to 5. So therefore, I am sure that this function has got a branching. This function has got a branching at x equals to 5, and so it will be x minus 5 when it is x is greater than 5, right? And it will be minus of x minus 5, sorry, right, when it is x is less than 5. I can't write it here, so just understand it. When it is less than 5, yeah, right. So therefore, mod of x minus 5, it looks again, as I say, it looks cute, but definitely it is not so. Whenever you have a mod function, be very careful that mod function always means it is a branching function. There is a branch, and first you need to identify the branch, and then you have to write it in the form of branch, and then you need to understand where you need to check for continuity and where you need not. So here also I can see, if the question would have been like examine the following function for continuity, and you would have been given this function, then obviously first you write it in this form, that is in the branch form. Now as I told you, any function is continuous in one of its branches. So for all the values greater than 5, it is continuous. For all the value less than 5, it is continuous. I forgot to put a greater than equal to here. So all the values, you can put the equal to anywhere. You can put x less equals to 5 also. You can put x greater equals to 5 also. Doesn't matter. But because at 5, it will always give you 0. So as I was saying, that in any of its branches, the function is always continuous. The only point where the continuity needs to be checked is at the branching point. So if the function is continuous in its branching point also, so I can directly say the function is continuous everywhere. But if the function does not remain continuous at the branching point, then I will say that the function is continuous at all the points except at that point. Fine. Or I can say the function has a point of discontinuity at x equals to whatever the point is. So now let us come back to our problem given. The problem is x by mod x. Now I discussed how the modulus function works. So my function here looks something like this. That is, it gives you the value minus 1 when x is less than 0. It gives you the value 0 when it is at 0. And it gives you the value 1 when it is greater than 0. Now clearly I can see that the left hand side of 0 and right hand side of 0 gives two different values. So it is not continuous. But we need to formally find the limits and show that it is not happening so. So let us do it. So left hand limit of the function to the left hand side of 0, it's minus 1, and the right hand limit of the function to the right hand side of 0 is 1. So once it happens so, I can see that it is not matching, and as it is not matching, so I can say the function is not continuous at x equals to 0, and therefore for the whole function, that is for the entire function, I can say the function is continuous everywhere except at x equals to 0, because the function will always be continuous in any other point, because all the other point remains in one of its branches, but x equals to 0 being the branching point, and as it is not being continuous at that point, I can always say that the function is not the function is continuous everywhere, but only leaving 0. Fine. So more or less this is our first part of the chapter. and we will come back in our second class discussing differentiability. So thank you.